Okay, so any questions in last classes? So after proving local minimum for a grid linear in order n time, so remember that the input that you were given was of size n square, right? So this algorithm is not just linear time, it is actually square root time, right? So in terms of the input size n square, this is taking only square root of n square many steps. So it's actually a sublinear time algorithm. Maybe we can write that term here. These things are rare. So in particular, this algorithm will not even use the whole input because it is sublinear. So for n input, it is for n square input, it is looking at only n things, roughly speaking. Then we saw binary search, which is in terms of input size and logarithmic. Right? This is even more rare because you are looking at exponentially smaller number of input bits. And GCD, on the other hand, is a linear time algorithm. So, obviously, to compute GCD of two numbers, you have to look at each and every input bit. Right, so that is the whole spectrum, logarithmic, sublinear, and almost linear that we have seen. So now we are in this problem of range minima, in which again you are given a 1D array of size n of integers, and given I comma j query, you have to output the minimum in that subarray. So the brute force algorithms are quite bad. So what we are investigating is this idea of focus on one index. So the first index I, and then only compute and store some of the j's, few of the j's. Right? So with j, so you take j to be power of 2. And then go from this I to I plus 2 raised to k. So basically this j minus I is equal to 2 raised to k. So only look at these pairs. So for every I, we will calculate all these j's. For all the k's, 2 raised to k. And we'll store that in a matrix, which is a small matrix. Okay, it's small in the sense that when you look at a row, the row has only log n many values. Yeah, so did you understand what is the connection between an arbitrary query I comma j prime and these kind of I comma j's? How will these I comma j's help in calculating or answering a query for an arbitrary j prime? Any ideas?
I think the idea is still the same that we used in the Fibonacci numbers, in which we summed up, we got to a number using binary numbers. Like to any arbitrary number using the sum of binary numbers.
Right, but when you are given a j prime, which is, let's say, so it is somewhere in the middle. So you have stored the minimum of I to I plus 2 raised to k. No, I shouldn't say the middle. Middle will remain power of 2, but say it is, you are interested in something just below that. So I minus 1 plus 2 raised to k. So that is just one less, or the position is just one less than what you have stored. So how will you now calculate that minima for that particular subarray?
Because we have stored all the previous numbers. Like if we want array 3,
but that is very far away. So I plus 2 raised to k minus 1, that is very close to I plus 2 raised to k, but not equal. and very far away from the previous one. So it is somewhere lying in the middle. No, don't tell me the time. I mean, what is even is there even a relationship?
So suppose we want the array of like 13 and we have stored 2, 8, 2, 4, 8, 16. So 13 can be expressed as 8 plus 4 plus 1, right? Which is all power to 2.
Mm-hmm.
And since greater than is an operation that commutes, that is works.
So are you saying that when we are looking at an element which is just behind the last one, which is I plus 2 raised to k, then to somehow capture that endpoint, shift I forward. So you should shift I forward and maybe go to I plus 2 raised to k, I mean I plus half of 2 raised to k, go there, and then that minima you somehow know. Yes, so basically you have to keep shifting the window. So when you are asked for the window of I comma j with the property that j minus I is a perfect power of 2, when an arbitrary query comes which is between I comma j in a bad position, then you should just shift the window forward or backward. Okay, so we'll shift the window and then we will need, I think, 2 kinds of windows to get the answer. Okay, just one window won't be enough. So we will see how that is done. So there is this relationship, that much now you have figured. So when the query is ij is arbitrary, we can reduce to a different query. Let's say I1 J1 and just read off B. So from the B array, we want to just read off answers, but it will not just be one answer. We have to probably access 2 places of the matrix B, and which will correspond to 2 different queries. Let's say I1 J1 and I2 J2, and then from that we'll try to deduce the answer of the arbitrary query which was not present in the matrix at all. Okay, so somehow we have to get this relationship. So this reduction we have to formalize. What is this reduction? So this will be called collaboration. So it is collaboration because somehow the answers for different I, let's say I1 and I2, those windows, those answers actually collaborate to give you the answer for this I comma j prime. So these 3 things or these 2 things are not independent. There is some correlation between them, and the job of your pseudocode is to actually formalize this correlation, how this actually works. So we have defined the tiny data structure, and one thing more I will need is define this max power of 2 function. So for a number L, this max power of 2 of the number L function, it will return the maximum power of 2 which is just below L. Okay, so this is this equals k, or 2 raised to k, this equals 2 raised to k, such that 2 raised to k is less than equal to L is less than 2 raised to k plus 1. Okay, so simply put, this max power 2 of L just gives you a power of 2 which is under L. Okay, so 2 raised to k can be equal to L or it can be smaller than L. But how much smaller? So can this L be so? Okay, so how to put this? So it can 2 raised to k be smaller than L by 2? No, right? So you can observe from the definition itself that this max power of 2L, it will be at least L by 2 and at most L. It's in that range, right? Because if max power 2L was smaller than L by 2, then you should have picked the answer 2 raised to k minus 1, which is a contradiction. So max power of 2L is just a power of 2 which is sandwiched between the number L and its half. Okay, this you can immediately read off from the definition. So anyways, we'll leave this function to describe the pseudocode.
Shouldn't that be greater than?
Yeah, if you want. But this is also correct. Okay. So let us, before giving the pseudocode, let us first draw a picture for the array. So your I is somewhere here. J is here. And this J is an arbitrary J, right? This is what the user has made a query. So this distance from I to J may not be a power of 2. So the real power of 2 is, maybe it ends somewhere here. So this is I plus 2 raised to k. And J just crosses that. So from here to here you have 2 raised to k. And then from here to somewhere ahead is 2 raised to k. So the problem is that this red cell, I comma, so this I comma that red cell, that minimum you have already pre-calculated and stored in the matrix B. And the next one you have stored is, it crosses J. So that's the other 2 raised to k, second one. And your J is straddling in the middle. Okay, so that value is not stored. I comma J is not, range min I comma J is not known or not yet calculated. And the user asks for that. So, so the simple solution is the following, that you should look at a window whose answer you already know, and that involves J, right? So it will be what? How do you get to that window whose answer is already stored in the matrix B and it involves J? Exactly. So you want J as an endpoint. So J as an endpoint, so that's the key thing. that you should be looking somewhere here. Because this is your j minus 2 raised to k. So you should be looking at this window, the blue one, because that answer is already pre-calculated and stored in the matrix. So it's j minus 2 raised to k comma j. So that answer you know, and there is another window whose answer you know, and which will be helpful, which is starting point I to I plus 2 raised to k. Right? So these two windows you know. If you know the answer of these two windows, what is the answer of the query? Minima, right? Because it covers all the elements. So that is it. So you use the blue interval and you use this interval. These are the two intervals. So intervals that start with I, which is I comma I plus 2 raised to k, and the one that ends with j. They collaborate to give I comma j. Right, because their minima is, first of all, their union is everything from I to j, and then their minima is hence the minima is equal to the minima that was queried. So this is what you can now turn into a pseudocode. So first thing that you should do is you should build the matrix B n log n, which will store the answers for j minus I equal to 2 power. Okay, so build that first. This is your one-time investment. It will take some time. We'll calculate that later. And once you have this this thing pre-built, now you can handle arbitrary queries. So range min a comma I comma j. So it will calculate the length of the interval, which is j minus I. And obviously we are assuming always that I is less than equal to j. So length is this, which is greater than equal to 0. And calculate the power, 2 power. So max power 2 of this length. So this gives you the 2 power which is sitting inside I comma j window. That's t. And k is log of this. That's the exponent. So at this point, we have the property that t is equal to 2 raised to k is less than equal to I, less than equal to L, which is j minus I, which is less than 2 raised to k plus 1. Okay, so that is the setting right now. So if T and L are the same, which means that j minus I is already a perfect 2 power, then you have the answer already pre-computed. So in that case, you should just return what? If you are awake, you would know this. What to return here? BIK, right? So BIK in the ith row, kth column, it stores the answer for I comma j in this case. So that you have already calculated, so you just return. Otherwise, you have to use collaboration of two different windows, two different subarrays. So you have to return the minimum of bi comma k, which is now not the final answer, may not be the final answer, because this is it's not really giving you I comma j, it's giving you something in the middle, just let's say partial interval, and the other partial interval is that ends with j. Okay, so the minimum of the two will be the correct answer. So that's the full pseudocode. Any questions? Okay, so if there are no questions, then we see the steps here. What is the time complexity? So number of steps in one query is how much? Log n. That's very expensive. Yeah, so no, maybe he's saying log n because of this computation of t. So there is this arithmetic that L, T and K will require. I mean, that arithmetic you can actually kind of already pre-calculate and store somewhere. You don't need to do it in every query. So don't worry about that arithmetic. We will only worry about the time complexity of this part. So range minimum actually, where you are actually using the array A, that is the data or the information or the input that was given to you in this particular problem, that information is being used only in this if then else part, because the B actually depends on A, which is the input. So here you are doing trivial things. This is constant time. So query is actually constant O1 time. Okay, so the query is as fast as possible. Every query you can, once you have the matrix B and some basic arithmetic already pre-calculated, you will be able to answer any query in constant time. So maybe one remark I can make here, that this T and K, or T rather, can be pre-calculated. You don't have to calculate it in every query. So the important thing is this if then else, and that is only constant. And what is the space? Storage space. So the space requirement here is as big as that matrix B. So it's n log n. Okay, so size of B is n cross log n. Obviously, B also has integers stored. Now, if the integers are very big, then storage space will also be very big. So that part is hidden inside big O. So if you want to also look at big integer storage, then you should see how big those integers are. If the integers are m bits, then you have to put m here, so it will be m n log n. But this part we abstract out because we don't care. I mean, for now, this algorithm and this data structure will not care about how big the integers are. If they are bigger, then proportionately bigger time, bigger space. So, keeping that in mind, the storage space is only n log n. Any questions till now? Because now we'll move to the harder part, which is how do you do the one-time investment? How do you build B in the fastest possible time? Okay, so what is it right now? So right now B is basically the Bij entry, just to recall. We just continue the proof. So Bij we have defined, or Ik, we have defined it to be the min of A starting I ending with I plus 2 raised to k. So for a given, an entry of I comma kth entry of this matrix B, how fast can you find it? By brute force you do a scan, so that will be order n. Right, so this takes order n. So, which means that as you go over all I and all k's, total time is how many i's, how many k's, and then order n for each. So this is going into n square log n, which is bad. It's okay for one-time investment, but not the best. Right, so this is taking n square log n time. Remember that it's not that much space. Space is much smaller. So in a reasonable space, somebody will invest so much time, and then the matrix B will be built. Right, that's the pre-processing. So the next question is, can you build it faster? Right, which means that you have to come up with this collaboration technique to build B itself, because you have to somehow find a relationship between I comma k entry value in the matrix with the earlier ones. So is there a relationship? Because if there is no relationship, if every I comma k answer is different, then you have to spend n square log n time, then there is no way. Right? So how do you verify that? Is there a relationship or not? Or is everything independent? So let's look at I comma k answer. So this is going from I to I plus 2 raised to k. And when you want to calculate something for I plus 1, then the cell will be this one. I plus 2 raised to k plus 1. So the old interval was this, or window was this, and the new one is this. Right, so do you see a relationship between these two windows? So if you know the answer for I comma k, what can you say about the answer for I plus 1 comma k?
We have to only compare I plus 2 to the power k plus 1 and the previous interval bi k. Minimum of that.
But we have to ignore the vi initial point.
Yeah, so it is not that easy, because the problem is that there is a change which is happening. So this one is removed and this one is the addition. So the first answer that you had, the minima, range minima for I to I plus 2 raised to k window subarray. If the minima resided in this black cell, then when you remove the black cell and add the orange cell, you don't know where now the minima is. Now it's again, you have to look at everything in the middle. Right? So there is this big subarray for which you have no information, and if you try to explore it, it will take linear time. There doesn't seem to be a clever thing here. So let's write that maybe. So bi plus 1 is equal to the min of by definition it is the min of I plus 1 to I plus 1 plus 2 raised to k, which is in turn min of this middle unknown part and the new cell. Okay, so this middle part, I plus 1 to I plus 2 raised to k, that is what is not yet calculated. So we don't know when the black cell is removed and the orange one is added, what happens? What's the new answer? Any ideas? How will you now go around this problem of linear scan? So the idea is to use the pseudocode. Okay, so although the pseudocode requires B to be built first, we'll now switch the philosophy. We'll actually use the pseudocode to build B itself. Right, so the pseudocode is a way to implement this picture where when you have a smaller interval, you try to find a collaboration, which is what we have implemented in the pseudocode. What it will mean here is that now this I plus 1 to I plus 2 raised to k, this is a smaller window. So the answer of this, what is the range minima query for this, can be answered if you have calculated the previous columns of B. The k minus 1th column. If you have an answer of the k minus 1th column of B, that answer with the pseudocode will give you an answer for this smaller interval. Is that clear? So you use the pseudocode to actually build B itself recursively. Because this minima is really, you can write it as min of range min of the window I plus 1 to I plus 2 raised to k. There is array also. And the last element, the new element. Right, so it is just rewriting this in terms of the range min pseudocode. So the range min pseudocode will give you the answer of I plus 1 comma I plus 2 raised to k. And the second element you already know, that's just one element. So the only question or the thing you have to verify here is, what does this take? If B is not built yet, how can we say that the pseudocode can be plugged in here? So the justification here is that the pseudocode only uses up to the k minus 1th column. Okay, so if you know the matrix B up to k minus 1th column, then you can compute the kth column. So this is the 0th column, this is the k minus 1, and this is the last is the new one. So this entry that we are trying to calculate I plus 1 comma k, this will reduce to the previous columns which we are assuming we have calculated. Okay, so the calculation will go from, using this idea, it will go forward. So you will calculate the 0th column of B, which is linear time, and then using this you will calculate the first column, then using the first two columns, third column, and so on. Okay, so this is the trick. So we gave a pseudocode assuming that B was completely calculated, but now to calculate B itself, we observe that the pseudocode actually works with very small b. So you work with small b, then make it bigger, and so on. So the pseudocode helps you to pre-process and build B itself. So which means that this step has complexity how much? So range min, assuming B, part of B has been calculated, pre-calculated, the pseudocode gives the answer in odd constant time, right? So this is order 1. So in constant time, you can calculate an entry in the matrix B.
So can you explain order 1?
Oh, order 1. Order 1 is explained in the pseudocode. This one. Number of steps in one query is order 1.
No, for calculating B.
No, but calculating B has been reduced to a query. The query is this. So it's a query for I plus 1, comma I plus 2 raised to k. That is one query.
But we need to go from 0 to
Sorry?
0 column to K.
No, we are not doing that yet. This is the induction step. So this step needs time constant by one query of range min. We always break the proofs into very, very small steps. So this is just one step. This is just one induction step. So here you are doing only one query. So that one query will just require constant time. Assuming that B from 0 to k minus 1 is known. So which immediately means that one column, or let's say the kth column to be precise, the kth column of B using the earlier ones takes how much time to calculate? Per element constant, so order n. To fill. Okay, so the kth column can be filled by these successive calls to queries, n queries, so order n time. And that means B can be built in how much time? So how many columns are there? So n log n. You get n times log n. Right, so we can actually we can do the pre-processing now in almost linear time. So this is an almost optimal solution for the range min problem, right? The data structure that we have used, it gives you an almost optimal solution. In almost linear time, you do pre-processing, and then in constant time, you handle one query. And the space that you need is also almost linear. So everything here is perfect. So you get the theorem after all this hard work that range min in a 1D array can be solved in n log n pre-processing. Order 1 query and n log n space. Okay, any questions about this? Yeah, so that basic idea that you had in the last question of the quiz, that basic idea gives you a brilliant solution here. But of course, you have to, I mean, you don't get this in the first attempt. There are multiple attempts to optimize this pseudocode or the algorithm. Okay, so yeah, any questions in the details of this before I move to the next topic?
How exactly does the algorithm proceed? Does it proceed like column? It fills one row at a time, or does it fill one column?
Yeah, so the way B is built is actually written here in blue. So maybe you read the middle statement that the kth column of B will assume, when you are trying to fill that up, you will assume that the earlier part of the matrix is already computed.
Okay, so it fills column by column.
Yeah, and it fills column by column, but you start with I equal to 0. First you find that, and then you use this green recurrence that we have written. So from I equal to 0, you want to go to I equal to 1. Yeah, so that can be remarked here. So if you want to see the full integrated pseudocode, I mean, I've only given you the fragment, so that the final pseudocode you have to write. So write the final pseudocode. But the way it will work is, first find so first you have to fill the 0th column of B. So that will be order n time. Wait. Well, even that. Yeah, so you have to again refer to this picture, how this was working. I mean, everything here needs some proof and some thinking. But anyway, so the steps just syntactically are these. You fill the 0th column using the recurrence. And then in the induction step, so iteratively or recursively, using the matrix from so this is all the rows, but the columns you are using are only from 0 to k minus 1. Okay, so the star means that you want to fill all these rows, but the column is fixed to be the kth column. And you have to assume that the previous part, so B star 0 to k minus 1 is already done. And here it is important that you carefully use the recurrence and hence the range min queries. Otherwise, it won't be possible. With this partial B. partially filled B matrix. Okay, so to calculate the kth column of B, you will need Rangemin pseudocode, the pseudocode that we have written for Rangemin query, which is constant time. And it will work fine because it only needs, whatever it needs is already available in the matrix. It will never query something that is unavailable. Okay, so that is why it can bootstrap itself. So with small matrix B, it can make it bigger. Okay, so it's kind of a bootstrapping that is happening.